is on the screen. I don't know if it's okay. No, you don't see me, but you see the screen. That's the best point. Sorry, so I don't start the right way.
Siguiente, next, the first one. First one, siguiente.
Okay. And maybe I will use this. Yeah. Okay, so we will briefly look at the new challenges and drivers for this new infrastructure, and especially for now mixing AC and DC grids into one unified power system. And we will discuss briefly that word of supergrid. Some HVDC fundamentals. The case of the new France-Spain interconnector, which will be in full commercial operation in June, but now the works are over, it's under testing. And the question of HVDC integration in AC grids, and the role of R&D, because in this changing world, you will see that there is still a need for significant research and development. So the current European power system, it's this one, where there are 34 almost interconnected countries, almost, because Iceland and Cyprus are not really interconnected yet with the neighbors, even if there are projects to interconnect them. On the contrary, Turkey is now synchronously connected to this European grid, and also a part of Ukraine. So 41 transmission system operators, one European institution, ENTSO-E, I briefly presented yesterday, and this institution is in charge of the pan-European grid planning, according to its legal mandate and the third energy package regulation. And the overall thing here is about, in the different synchronous areas, about 820 gigawatt of installed capacity, a load of 3,300 terawatt hours. You see that the annual exchanges of electricity are quite limited. There are about 10% of this. If we discuss only the backbone of the grid, so the main infrastructure, it's about 300,000 kilometers of HVDC circuits. And this is to serve 500 million inhabitants. So this is the grid of today. In red, you have the 400 kV lines, and in green, the 220. You see that in some areas, the political borders are still visible, just looking at the grid. In some areas, it's a bit more meshed, but this is the current grid, where the infrastructure has been developed country by country with interconnectors. When we consider the grid we need for the year 2030, most of the 2030 grid is there. It's this one. 90% of the grid is already there. Sorry. Yeah, here it is. Okay. So this grid is already there. And there will be significant changes because of that need to adapt to the new generation pattern. On the other hand, the load will probably not change drastically. It's quite unlikely that Frankfurt will move 300 kilometers east. So the main consumption centers will stay at the same point. So the in-feed grid will probably remain as it is. What's now necessary is to create the condition to use efficiently the new generation and where it's located. So again, most of the current of the future grid is there, but it's like with the DNA of human beings and monkeys. You know, we share about 99% of the DNA, but at the end, the 1% makes a difference, and it's a bit the same for the grid for 2030. So this is a picture which is popular in an association. RTE is a member of this association, which is called Friend of the Supergrid, FOSC. And this is the poet's vision of what should be a supergrid. It's really nice. It's part of reality, but it's only part of it. When this word supergrid was made popular, I think many people had the idea that this was an entirely new grid. I could hear people saying that could be a 1 million volt grid. Well, good luck if you consider how it's difficult to build 400 kV grid because of electrical fields and towers size. And when you look at some countries have grids at 1 million volts, there are some lines in China, there are some lines in Russia, not really in operation now. It's good for areas where there is no population. There is another issue with ultra high voltage facility. If you build a 1 million volt line, it's very good because it replaces, let's say, 4 normal circuits. But you have a problem. If this line fails, then the lack of security is really huge. So it's strictly not interesting to build one. If you build one, you have to build 2. One for being the N-1 security of the other. And 2 is really not enough. So there is a huge quantum gap. If you want to go to 1 million volt, you have to build a whole set of infrastructure. In Europe, I think this is extremely unlikely to happen. So hopefully there is another solution to build new heavy transmission facilities, but the possible emergence of a supergrid with ultra high voltage is extremely unlikely. And this is an understatement. On the other hand, there was the idea that supergrid would be something like an upper level grid. At the time, there was a familiar expression which was overlay grid. You know, that kind of grid which was operated in hierarchical way from the current one. And again, this doesn't fly. And this was a concept which was more a lobbying concept and sometimes a power game, because the idea was that this supergrid could be operated by one single European operator, not by the different current transmission system operators. But the reality of this has faded away. So we will have a supergrid, but this will be the grid of today, with a number of new facilities, new interconnectors, making this current grid more flexible, more adequate to the future of the energy mix, and really fit for the future of the European electricity. So the new challenges and drivers, you know this, the new target, which have been total consensus of the member state, the head of states, minus 40% CO2 emissions, 27 renewable energy sources, and 27% energy efficiency, which means about 45% of renewable energy sources in generation for electricity. And that's a huge gap from the current situation. The natural resources are not dispatched everywhere. Hydro is located in some European areas. Here there is Norway missing, and Norway is one of the big hydro generator. And wind and solar are not everywhere, and should be incorporated in a smart manner to avoid a huge overcost and loss of competitiveness in Europe. This is an EWEA, the Wind Association forecast for the year 2030. And you see that the onshore wind development will saturate a bit when we go further into the century. On the contrary, offshore grid development will still be pushed. The offshore resources are not also equally spread all over Europe. To develop offshore wind at a reasonable price, you need shallow water. And for example, the Mediterranean is not a good place to develop offshore wind because in many areas the depth of the sea is immediately much too high. On the contrary, the North Sea is an excellent place because it's a shallow sea where you have a lot of sandbanks, and a lot of the North Sea has depths which are between 20 and 50 meters, which are suited for offshore grid development. Also, the Baltic Sea is a similar one, and those two places are concentrating the most of current offshore wind development, even if there are some extra places where it happens. So if we have a look at countries who have developed a lot renewable, that's Germany. With the year 2000, you can see that wind has already started being implemented, and some biomass also. And if you look at the situation 10 years later, and I don't have the picture for 2015, but it's probably all red and yellow, you see that the development of renewable is now considerable with, well, two different regions, the north with wind and the south with solar. And with, of course, two different and separated and not correlated weather conditions to generate. If you look at this map of Denmark, you have some red dots here. This was the generating plants 10 years ago. So they were located in a few places. Now you have all these dots are the major wind farms in Denmark, and you can see that this has totally changed the pattern. And these are very small units, but when the wind blows, they generate an overall huge power, which will bring a number of flows across Europe. There are some nice curves about the exchanges between Denmark and the northern Scandinavia, especially Norway, where you can see one day with a strong wind, the wind blows at about 70, 80 kilometers per hour, and Denmark, which is basically wind and coal, if I exaggerate a little bit, and some combined heat and electricity generation. So there are huge flows going from Denmark to Norway. Then the next day, the wind blows a bit more, and it reaches 90 kilometers per hour. And suddenly, all the windmills here are stopped for security reasons, and you see a very sudden change in the flow pattern, with suddenly huge flows going from Norway to Denmark. And this is the way it has to work. This is solidarity, but it has to be organized. And these huge flows here are the condition to really take the best advantage of renewable sources. And having this type of flows is new in Europe. So today the situation is the following, with a number of bottlenecks. There are bottlenecks between price areas, bottlenecks within price areas. Some are under strong monitoring by a number of regulators and parties. For example, the bottlenecks within Germany, which are a topic for controversy within Europe. Should there be one or two price zones in Germany, and how to handle this? But there are also bottlenecks within France and within many other countries. And you have also bottlenecks due to strong new connection of generation. This is the case for Ireland, for example. Ireland is currently a country which, in the perspective of 45% of renewable electricity in Europe, says that they have to take a big part of it, not only their share. They say that offshore wind is just stupid because it's extremely costly compared to onshore wind. Of course, the costs are decreasing, but not so quickly because there is a lot of civil works and you have to dig your pillars into the sea. And they say we are the offshore platform of Europe. In the heart of Ireland, in the central region, there are huge desert areas. This is peatland. It was used for peat, you know, is a kind of earth you can burn. It's not exactly environmentally friendly, so it was decided to stop this as a source for power generation. So there are huge surfaces of land, nobody to complain, and the winds are exactly the same as on the ocean. So their point is just build onshore wind mills here. You will have the same condition that offshore windmills, much cheaper, and then you just have to build the cables to the continent. And this will be a much cheaper way to generate power than to build a lot of offshore wind farm in the Baltic or in the North Sea. It's a bet. It's what they are trying to set up, and we will see if they succeed. But it's quite likely that they are successful on this, and we will see later on that there are already a number of interconnectors being developed in that purpose. But so if we simplify a bit this map with a number of bottlenecks, what we can see, there are 4 regions which are not well connected to the heart of Europe. One is the Iberic Peninsula, one is the British Isles, Italy, and the Baltic states, which are very well connected to their best friend, which is Russia. And they have a small tendency to say that they would like to be connected better to other friends, which are basically Finland, Sweden, and Poland. And don't forget, there is here that white area is Russia. It's the Kaliningrad area, which is a part of Russia, which is embedded in that part of Europe. So, of course, you can see that geography is the main explanation. Here you have mountains, here you have mountains, here you have oceans. So, what does this energy transition require? I think that I mentioned this yesterday, new hardware, new software. I think we should not underestimate the new software. I will not rediscuss this. This was yesterday's discussion. But for renewable, we really need to have a development of the market design and the software to integrate adequately the renewables. It will not be efficient with the current system. So the investment is 50,000 kilometers of new transmission line compared to the 300,000 existing ones. So you see, it's significant, but it's not a total redesign of the grid. There has been a lot of discussion within Europe about the right level of interconnectors, and I have to say that these questions have been extremely active thanks to Spain and Portugal, especially. There are different visions on this. One, there is an engineer vision, which is whenever an interconnector brings significantly more social welfare than it costs to the collectivity, to the consumers, it has to be built. If it costs more than the benefit from the customers, you should not build it. That was the basic thing. And in the 10-year plan, the investment plan set out by ENTSO-E, this is the rule for every interconnector. There is an economic assessment, what the value brought to society, what the cost for the society. If the value for society is much higher, is higher than the cost, well, it's put into the plan, it has to be built. Spain and some other countries, basically the Baltic countries, have another view, which is there should be a minimum figure. Which is 10%. There has been an agreement that this could be considered if it's a minimum figure, because you cannot have one size fits all thanks to geography. For example, Denmark today The interconnecting capacity of Denmark is already 100%, and it's not enough. But I have to say 10% of what? Because this is part of the debate. If I say, and this is something which is rarely discussed. People are fighting, it should be 10%, it should be 15%, no, it should be less, but nobody discusses what are we talking about. We are discussing here the commercial exchange capacity versus the installed generation capacity. And this threshold was set up the first time by the Spanish Commissioner for Energy, Mrs. Loyola de Palacio, that was in Barcelona, 2002. And at that time, the typical ratio between installed capacity and the peak demand was about 1.3. So you have 30% more installed capacity than peak generation, and this is to cover all the possible incidents or probabilities you may have. Today, with solar power and wind power, the ratio is more. It's not 1.3. It's about 2 or even 3. So if you still take this figure into consideration, then the commercial capacity to fulfill the 10% criteria really is increased considerably. However, there has been a discussion, on those 10%, agreed for 2020, agreed but just impossible to reach. It's too late. When you are in 2015 and you decide this for 2020, you just have your tears to cry, because it's too late. It takes at least 7 or 8 years to build something. So this is a reasonable target, let's say, for 2023. This is achievable. But 2020, very unlikely to happen. Then the point is, should we aim at something different in 2030? It's shivering more and more, but I don't touch anything.
It won't happen the same.
Okay. Yeah, probably. So 2030, maybe a 15% threshold, which will bring more interconnectors to the Iberic Peninsula and the Baltic states, which are the two countries which have this target in mind. So the 10-year network development plan, this investment plan, how it works, you have a pan-European expert group which is set up, and it runs cost-benefit analysis with a methodology that has been approved by stakeholders, approved by the Agency for Regulator, with a multi-criteria approach, and with a permanent involvement of stakeholders, and possibilities for any party which has a project for interconnector to bring this project to the plan and propose it to the plan. And from this plan, which is finally approved, the European Commission extracts a number of so-called PCIs, projects of common interest, which benefit from special facilities to be built as soon as possible in the best financial conditions. So you have a number of embedded plans. Each country has its national development plan. There are regional reports, regional in terms of clusters of countries. Then you have the 10-year network development plan, which is the infrastructure which has a pan-European relevance. And this is really planned as one single grid, whatever the political borders are. And from this, the Commission extracts the project of common interests. So this is an example of the current PCIs, and you can see that there are some who are here on the borders between Spain and the rest of the continent. These are DC links, this is a phase shifter, and these are links with Portugal. You can see also there are huge projects, so the one of interconnecting Cyprus to Greece on one hand and to Israel on the other hand. That's also some politics. Probably the rational engineering should be to connect Cyprus to Turkey, but you may understand that the political conditions are not there to do so. A question when you decide on the future infrastructure is to connect what will be the load in the future and what will be the generation. And 2030, it's tomorrow for an infrastructure, but it's far away for deciding the state of the European economy, for example. Will the European economy boost in 2030, or will the crisis be longer than expected, as it has been the case? There have been many reports that were predicting that from 2011 on, the whole Europe will recover very quickly from the crisis, and unfortunately, reality has been significantly different. So when you try to set up the right level of infrastructure, you have to take different big scenarios. And there are a number of scenarios which are discussed with the parties. They have names which are supposed to be self-explaining: green revolution, money rules, slow progress, green transition, where there is a crossing of integration of European electricity market and the development of renewables on track for energy roadmap 2050 or not on track. And in the background, the current health of the European economy. And with those different visions, you build different European grids for the future. And then you check what are the differences and the similarities. And hopefully, when you look at this, the grids for these four scenarios, you see that a number of facilities, a number of infrastructures are necessary anyhow. They are the no-regret options. You have to do them anyhow. And some others are more or less necessary according to the scenario which will happen. In fact, you can be sure of one thing: none of this scenario will happen to be reality, but reality will be somewhere within that set of scenarios. So the result of this is these 150 billion euros of projects which have to be built by 2030, which a very good return on investment for the European citizen, 20,000 kilometers of new infrastructures, and CO2 reductions and accommodation of up to 60% of renewable if it's well placed. But with that result, everything is not solved. When you look at the infrastructure which is worked out in this plan, you see that in some cases, that's for the borders of Italy, for example, in all those four scenarios, it's okay. There is enough infrastructure. In some other cases, let's say France and Germany, well, it's adequate in 3 out of 4, but there is at least one vision where it's insufficient. And you have one border where, because of the lack of project, in no scenario it's adequate. So that means that the border between Spain and France, Spain and the rest of Europe, is by far to be developed in terms of infrastructure, and the current projects, the one who is being commissioned and the new one through the Gulf of Biscay, are not sufficient. So the main obstacles to get this becoming reality are the public acceptance. I think yesterday I've said something about it. It's really necessary to explain again that you can't get a very effective climate policy and very effective renewable development policy without infrastructure. That will not work. And if you want renewable without infrastructure, you will have the cost and the CO2 emissions. So it's not exactly the target of the European policy. Permit granting is key. When we look at the 10-year plan, the investment plan that was published in 2012, so now 3 years ago, 1/3 of the project are already delayed by more than 2 years. So this is just terrible, and we will not make it if we don't address this question. And the PCIs, the European Commission has tried to address this. Unfortunately, the answer by the member states today is not exactly the one which was expected. And financing is also an issue. because it's a long-term investment plan, you need a stable and adequate regulatory framework. Again, this is a challenge. In many countries, the national regulator considers that his main duty is to decrease the transmission tariffs, it's to decrease the price of electricity paid by the consumer. I think the idea looks very nice, and I think we can all agree on this. Depends on what is the time scale. If you decrease the electricity price today to have a huge increase tomorrow, maybe it's not a good policy. And maybe it's better to increase a little bit now to have a low electricity price in the future. But if you are a regulator and you have a 5-year mandate, and you know that you will be assessed at the end of your mandate, that may be a temptation to reduce the price now. And well, the future will be the story for the next colleague. In this respect, especially the transmission system operator call for an increase in powers of ACER, the agency for coordination and cooperation of the European regulators, for ACER to impose to national regulators, where necessary, a framework which will allow the investment to happen. On the short term, there is a huge effort by the European Commission to bring what's called the Juncker Fund, which is a small amount of money resulting in more than 300 billion euros when you take into account all the effects of secure and efficient funding by the European institutions. That will be a trigger probably for the investments in the coming years. But the Juncker Fund is for the next 3-4 years. And again, you will spend money in that 3-4 years period if you have started your project 5 or 6 years ago. For a totally new project, it's too late. You will not be on time to use that money. So when you think that it's almost impossible to develop new overhead 400 kV link, you come to a solution which is DC. DC overhead, DC subsea, DC underground. And then we have a totally new physical transmission system where HVDC is not only the border between non-synchronous systems, it becomes totally embedded within the AC system. This is an example of one of the challenges for the next years in Europe. It's the development of the so-called German north-south corridors. And 4 of them are HVDC with 8 gigawatt, which has to be developed between the north and the south of the country. This will be mainly built by using existing AC corridors of towers. I'm not totally sure that at the end of the game it will not finish by underground cabling along freeways. But this is still a hot topic for discussion. Underground and submarine cables will be more and more many, and power electronics will be everywhere and change the way to control the security of the grid. So I will come back to the outcomes of this later on, but some recall. I think many of you are familiar with HVDC fundamentals. Well, that's a bit historical. You know that electricity 130 years ago was a battle between 2 men. Thomas Edison was the one who was sure that DC will be the support, the vector for electricity in the coming century, and invented the incandescent bulb, and he started the first DC distribution grid. And his competitor was George Westinghouse. He was thinking that AC will dominate the electricity world, and he started importing transformers, which were key to develop the AC power grids. Hydro generators, and it's easier and cheaper to develop a generator in AC than DC. And finally, let's say at the end of the 19th century, it was considered that Westinghouse had won the battle. maybe it was a temporary victory. But for the 20th century, for sure, the 20th century was AC. When we look at DC versus AC now for new big infrastructure, what DC brings is a better control of power flows. With an AC system, you don't control anything. You may control the topology to some extent, and that's it. So the flows goes where the Kirchhoff's laws ask the flow to go, and this is a typical electrical engineer joke that you probably know, that in with different countries, according to different storytellers, that some parliament members say, well, Kirchhoff laws have to be amended, bring them back to the parliament. But doesn't work, and so the physics just have the major part, while with DC you can control the flows. It brings a stable connection of asynchronous networks. For example, between France and England there is a 2 gigawatt link, and when the studies were made in the late 60s, there were also ideas to have an AC connection, but the AC connection was unstable. It was like if the whole Great Britain was a huge generation machine with a weak connection to the big grid, and it was just statically unstable. It allows to connect AC networks operating at different frequencies. The best example is South America and Japan, which is cut into two parts with 50 Hz and 60 Hz. The transmission capacity of lines and cables in DC is better used because you don't have reactive power. And you know that on underground 400 kV cables, after, let's say, 40 kilometers, you overheat the input while you don't have anything at the output, because all the electricity flow is used to supply the big capacitor that the cable is finally. You use less copper, which means that it's less expensive. And if you use DC overhead or DC underground, you have a smaller environmental impact. And I would say this is especially true for underground cables. If you have 400 kV AC cables, neutralize a huge band of land where you can't have trees, where the soil is sometimes hot, and it's extremely difficult to get this accepted by the farmers and the agriculture community. A drawback for DC links is that they need converters, and if you have a line of 0 kilometers, you have still to pay for the converters, and they are expensive. They are expensive, and so if you compare the investment costs and the cost of losses with DC and AC, you see that with DC, even if a transmission distance which is 0, you have already a significant cost. You have break-even distances, and those break-even distances, well, they depend a lot of the technology and the sizing of your facility, but it's about 40 kilometers for cables and 500 kilometers for overhead line. Overhead lines are cheaper, so the weight of converter station is higher. What are the costs we are talking about? And these are some examples of some interconnectors or facilities developed by RTE. So for the France-Spain on in the Catalonia side, it's 2,000 megawatts. The cost is 700 million euros. The cost of converters is about 150 million euro each. So you have two converters, of course, so it's a bit more than 300 million euros. This one, 2 times 600 megawatts, so slightly lower power, a bit smaller cost for converters, higher cost for the facilities. So you see some orders of magnitude which shows that for big project, it's typically not far from 1 billion euros for a single infrastructure. So this technology is booming all over the world. You have new facilities and existing facilities all over the world. But if I take that look just at this corner of Europe, and when you look at what is forecast for 2030, you see that there are a number of cables which have to be built. So this one, for example, between France and Ireland, which is called the Celtic Interconnector, it's now scheduled for 2023. You have currently 3 projects between France and England, one through the tunnel under the channel, and 2 other interconnectors. The English regulator has just given its green light at the condition they are built before 2020 for the 3 projects, these 2 ones here, and these ones between England and Denmark. But you see 2 projects between Norway and England. And you see also what National Grid called bootstraps. Those cables here, and here, and this one here, they are internal links. It's just totally impossible to cross the highlands here. They have tried for many years, probably like the current France-Spain interconnector. This is a story of 20 years trying to cross the highlands. Now they have given up. And it will be an undersea cable here and here. This one is currently delayed because they, laying the cable, they have found World War I submarine, which is exactly where they had to build the cable, and so there has been a request to stop for the moment the works to send archaeologists to this place. But this will be built, and you see how it develops. You see also the challenges of the North Sea. Here in gray area, you have the areas for development of offshore wind. And one of the questions, and one of the typical super grid question, is what should be this grid looking for? Like this, with bilateral links between areas, or should it be a meshed DC undersea grid, which is currently strongly pushed by a number of parties? You see that currently the choice of transmission system operators is to have these bilateral links, and this is not by conservatism for once. I will probably explain about it. You have 2 main technologies for DC links. The old technology, which is called LCC, line commuted current source converters. And this technology uses semiconductors like this one. This is this size about. And these are thyristors. And they have been used for decades. The 2 gigawatt link between France and England was built in '86. And these converters had to be replaced just before the Olympic Games, because this in London. So this means that after 25 years of good service, they have to be changed, but they were used efficiently. The new technology is based on transistors. It's voltage source converters, and it's much more powerful. This technology has a number of advantages, because with force commutation you can really have a power electronics that does what you want. The source behaves like a voltage 1, and to change the flow of the power, you don't change the polarity of your cables, which is a cable killer. You just change the direction of the flow on the same cable. So that makes it possible to use cables without oil, which are more cost-effective and more environmental friendly. While LCC links absorb reactive power, you need huge filters to supply reactive powers. For this one, they just do whatever you want them to do. They are less sensitive to voltage dips. And well, one small drawback is that the fault clearing is a bit slower with that technology. You have different technologies to achieve the conversion. This is pulse width modulation, and these technologies are more or less linked to a manufacturer. This is the ABB technology, while this one, modular multi-level converter, is used by Siemens. And this technology makes it possible to convert DC into a sine wave for AC. So if you look at the system operator viewpoint and the interest for this, this technology is very interesting for power inversion flexibility. You can invert the power very quickly at any time without aging your facilities. It brings you new possibilities for voltage control. It has excellent stability. You can build a control which does whatever you like. And it also includes black start facilities and frequency control. And this is extremely flexible and efficient. So just at the moment, in my country, where we have put into service a double circuit overhead AC 400 kV line 2 years ago, in a totally new place, we have no project of this kind any longer. All our big projects are either to upgrade existing facilities or to go DC underground or subsea. So you see this one being commissioned. This one, well, the geography is not really nice. It's between Bilbao and Bordeaux. This one is being built at the moment for a service in 2015. This is Celtic Interconnector, 2023, 2025, and these are the two new ones, and here again a new one. And this is for interconnectors. But we also have a project which is a totally internal project because we have to reinforce the transmission grid between southeast France and southwest. And it's just impossible to build anything from here to here. When you look at a map of protected areas, you can't find a path. It's just not possible. The only way is to go subsea and then underground. And that's the project which is under work currently. So some pictures of the brand new interconnector between France and Spain. This is the device to dig the tunnel. This is the undergrounding. This is the cable and the technology. So it's 320 kilovolts, which is the highest currently available technology for this type of cable. A tunnel, a special tunnel for 8.5 kilometers. So you have here some views. This is a view of exactly the border. You see the border between the two countries is here. It has to be materialized. This is a converter station on the French side. You see, it's not, you know, a small cabinet in your kitchen. It's an interesting facility. And again, the different facilities. So this one was built by Siemens. So HVDC integration. There are 4 stages in terms of complexity. The first one, the old one, is you connect synchronous systems which are not you connect asynchronous networks. They're not operated synchronously. That's the France-UK interconnector, for example. Or you interconnected 2 synchronous countries with a very weak link. For example, this one between Italy and Greece. The electrical distance between the 2 points is huge. So this is pretty easy. More recently, you implement several DC links which are close to each other. The France-England link and the Netherlands, this is 2 gigawatt, 1 gigawatt between Netherlands and England. Then it becomes a bit more tricky because here in that area you have the 2 converters very close to each other. First stage, where we are now, you have DC links embedded in the AC network, and this brings new challenges in terms of control. That's the link between France and Spain with the existing AC lines, the one between France and Italy, this one I mentioned. And you have a 4th stage, which does not exist yet, and it's a current design, which is HVDC meshed grids. So when you operate HVDC embedded in AC flows, you have a number of very interesting facilities, which I already described, that give you a number of opportunities. But it requires much more complex assessments in operational planning. You have to really decide together how you set those links. Those links, you can tune everything. So you have to talk to your neighbor before tuning. If not, you may have very interesting properties for you and catastrophic properties for your neighbor. So the increased coordination is really necessary. Sorry, and you also need a sophisticated coordination between neighboring converters because they are not independent. And then you see this type of new development where when you have neighboring HVDC links, each has its primary control. There is a secondary control to ensure regional coordination and a tertiary control to optimize the operation of the whole system. So it's the old trick of engineers when you have a very complex problem, you try to solve it with a hierarchy of controls, local, regional, and global, with different time constraints, some seconds, some minutes, and about 1 hour. And this is a field where really there are new developments to be achieved, and this will be very serious if we don't address these points correctly in the coming years, because we will have disappointing results. France-Spain link is a good example. Currently, there are still, let's say, reasonably hot discussion between RTE and Red Electrica. How should we use this new link? To make a caricature, RTE viewpoint, it has cost 700 million euros. We should use it full speed ahead in one direction, full speed ahead in the other direction according to market condition, but we just use it, 2 gigawatt when the market asks to. Red Electrica viewpoint, well, this will bring completely new operational challenges with possibly pushing the power here and the power coming back on the other side of the border. And we should use the flexibility of VSC to emulate an AC interconnector. So it's DC, but you can exactly use it as if it was an AC interconnector reacting to the angles and the flows. I'm sure we will find a solution, but this shows you the new variety of situation and solution, where at the end you have to operate. One thing for sure is impossible, that RTE sets full speed ahead and Red Electrica decides that it's emulating an AC circuit. That will not work. So further development is really needed in that coordination, innovative control. And there will be other challenges which will be needed to be met. Very quickly, the role of R&D. You need for this, you have to control, you have to anticipate what happens with these new extremely nice toys, and you need totally new simulation tools, or you need a variety of simulation tools, because you have to address all the typical time constants for voltage stability, transient stability, electromagnetic transients. And this is, currently there are still some difficulties with some offshore wind platforms, where the interactions between the platform and the HVDC converter to go onshore bring some oscillations which were not anticipated and just create a very difficult problem for the hardware. You cannot do these simulations totally on your computer, because typically you need to test real controls. These real controls are typically confidential. They include confidential algorithm, and you really need to test the existing hardware. So the only thing is to use a real-time simulation platform where you really interact with the actual equipment to see if its answer is exactly what you were expecting. But RTE has developed such a laboratory where you can really test the behavior of the control as it would be. A missing element is the chain, is the DC circuit breaker. To have a meshed grid like this, you need a DC breaker, and it does not exist yet. at the rating value which are required. So what's needed is 320 kV and a lot of amperes. What's today is 160 kV and the most advanced prototype. So it's not that far. It's obviously feasible, but it's not there. This is a prototype built by Alstom. And you see it's not exactly the thing that you put in a small box at the bottom of the North Sea at the moment. Also needed improvements in softwares, and I mentioned this project EIWay 2050, which is for developing methods for the planning of the grids and deciding which are the best infrastructure and their technology. These pictures to show you these projects are now so huge that they have to be pan-European, and you have a number of partners to this. It's now time to pool the efforts. Nobody can carry out such a project alone. No institution, no company in Europe is big enough and powerful enough in terms of research and development. So maybe our next challenge is 100% DC grids and the final victory of Edison. But this is a totally new chapter of electrotechnology, and all the young people in the room, maybe that will be your work for tomorrow. So in order to ensure sustainability, competitiveness, security of supply, we need a real thrust in infrastructure development, a market redesign, and more R&D and innovation. Challenging times, very happy times for power engineers.